Last time we slid retrieved chunks into the prompt and waved at find the nearest vectors. But how does a database find the nearest of 10 million vectors without comparing against all 10 million? Start with what an embedding even is. The model has learned a space, picture a vast star map, where every piece of text is a point and meaning becomes distance. Cat and kitten are neighbors. Cat and quarterly tax form are on opposite ends of the galaxy. That's the whole magic, similarity turned into geometry. So search is dead simple to describe. Embed the query, drop it on the map, grab the closest points. The hard part is closest. Doing that exactly means measuring distance to every single point. At 10 million points every query, that's hopeless. So we accept approximate answers, get the closest points almost always, in exchange for enormous speed. And that trade is governed by a triangle, 3 corners, recall. Did you actually find the true nearest neighbors? Memory, how much RAM the index eats. Speed, how fast a query returns. You can be great at any two. You cannot max all 3 at once. Every index structure is just a different point inside this triangle. The real systems have a couple of clever twists. Cursor doesn't just embed code generically. It mines its own past agent sessions, has a model judge what should have been retrieved at each step, and trains its embedder to match those judgments. Retrieval tuned on its own behavior, not on generic similarity. They report about a 12.5% accuracy lift, and it stores all that in a remote index turbo buffer that resyncs changed files every few minutes. Let me show you the 4 index structures as one morphing diagram so you can feel each one slide around that triangle. Start at flat, no structure at all. You compare the query against every vector, brute force, perfect recall, no build step, but it's the slowest and it scales horribly. This is the right choice under about 10,000 vectors, or any time exactness is non-negotiable. Now morph to IVF, inverted file, cluster the vectors into buckets ahead of time. At query, only search the few buckets nearest the query, not all of them. Cheap memory, fast build, but recall now depends on how many buckets you probe. Probe too few and you miss neighbors that sat just across a bucket line. Morph again to HNSW, a navigable small world graph. Vectors become nodes wired to their neighbors in layers, and a query hops greedily down the graph toward its target, like skipping across a friend of a friend network. This is the best speed to recall point in practice, but it's slow to build and hungry for RAM because you're storing the whole graph. Last, PQ, product quantization. Compress each vector down to a few bytes by snapping it to a codebook. Suddenly a billion vectors fit in memory. The cost is recall. You're searching lossy approximations of the originals. This is the corner you go to only at 100 million to billion scale. Which database wraps these up? 3 honest answers. Fuzz is the raw library, 10 plus index types, GPU support, maximum control, maximum engineering effort. Reach for it from a few 100,000 vectors up into the millions. PedVector is the try this first if you're already on Postgres. Your vectors live right beside your relational data and get queried in one transaction. Chroma is the friendly embedded option for 10,000 to a couple 100,000 vectors with metadata, and one production gotcha for all of them. Filter by metadata after the index scan, and you can come back with too few rows. The scan didn't know about your filter. So now you can build a fast index and a static top K lookup, but the fastest moving coding agents are quietly abandoning that lookup entirely and just searching the repo live like a human would. Next, static RAG versus agentic retrieval, the central harness choice. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.